Imagine you live next to a coal plant. Every day you breathe in dirty, polluted air. You go to the EPA to tell them to stop it, but they don't believe the air is bad. They don't believe you because you have no measurement of air quality to prove it's bad. You have no measurement because you have no air quality sensor. So the coal plant keeps polluting your air because you couldn't prove the air was bad, because you had no measurement of the air quality. This terrifying scenario is an unfortunate reality in power systems with the harmonic problem. This is what our project, Harmonic Measuring Modeling for Transmission Applications, sponsored by ITC, explores. So, harmonics are pollution in the 60 Hz power system. Harmonics are waveforms with a frequency that is a multiple of 60 Hz. These harmonics cause flickering lights, overload transformers and motors, and damage electronics. In the modern grid, inverter-based resources and nonlinear loads are the main cause of harmonics. Transmission sits between these sources and loads, so to measure the pollution, we should measure it in transmission. Luckily, we do have an air quality sensor. Coupling capacitor voltage transformers, CCVTs. CCVTs are a capacitor voltage divider cascaded into a magnetic transformer. Due to the reactive elements in the CCVT, the harmonics are filtered out at the output. Luckily, our customer ITC uses the Temp 145 CCVT, which has the Trench Harmonic Monitoring Device, or HMD, which does not filter out the harmonics. So this is our air quality sensor. But not all Temp 145s can do this. Old units do not have the HMD installed. Factory installing the HMD on old Temp 145s is difficult and costly. So what if we can measure the harmonics by field retrofitting the HMD or another device, the Ritz Power Quality or PQ Sensor, and avoid the arduous process of sending the Temp 145 back to the factory? Since we do not have a Temp 145 to test retrofitting with, we will be modeling a Temp 145 CCVT and then harmonic measuring devices to evaluate the performance in measuring harmonics. Using transient software, ATP, EMTP, and PSCAD, we modeled the Temp 145 based on documentation and academic papers. However, to get the most accurate model, we changed our model parameters to match frequency response data of a real Temp 145. In the end, we were able to accurately model a Temp 145. Moving on to the devices, we used an LRC meter to find that the HMD was just a 6.1 microfarad capacitor, and we also found its ESR and ESL. In our test with the PQ sensor, we found that device had to be tailor-made to each CCVT it was placed in. Our customer contacted the PQ's manufacturer and found that it could not be made for the Temp 145s. Using the RLC equivalent of the Trench HMD, we added it to our model of the Temp 145 to simulate its performance. We found that the HMD performed well within IEEE standards, even with changes in load, capacitance values of the divider, and even changes in the wiring. However, long cable lengths from the HMD to the control house can make the HMD's performance much worse. So, it is our recommendation that the HMD should be retrofitted to old Temp 145 units, with caution taken with long cable lengths. Unfortunately, there are limitations to our findings. Our model cannot account for real-world problems such as moisture and temperature. We must keep in mind that this model is a best-case scenario in that regard. It is also worth noting that the HMD's performance gets worse nearing 10 kHz. Should standards update to stipulate that we must record higher order harmonics, the HMD will be made obsolete. Special thanks to the team at ITC, Esther Beaudry, John Palan, Cordy Holt, and Jacob Grant. Our advisor, Professor Hassel, Professors Pinar, Costa, and Mort, graduate student, Shadi Al-Shagari, laboratory supervisor, Chuck Sanas, and research associate, Mark Swift. Without them, this project would have not happened.